if I don't use it. So I recommend, this is lecture 12. We just started, and we will continue discussing about things that utilize the 4 fundamental subspaces that we saw in the last several lectures. So what I want to remind you is the fundamental theorem of linear algebra says, the first part says things about the dimensionality of the different subspaces of a matrix A. So remind me, what is the dimensionality of the column matrix, of the column subspace? R. Of the row space? R. Of the null space? Say it again. N minus R. And of the left null space? M minus R. And you should always remember which subspace is subspace of Rn or Rm, right? So like if you look at the columns, they are Rm, so obviously the column space and the left null space, they are in Rm, but the row space and the null space, they are in Rn. Correct? Okay, so the first part of the fundamental theorem defined the dimensionality, and most importantly, we discussed that these spaces, they're orthogonal, and even better, the word we use beyond orthogonality was what? The null space, for example, the row space, what are they to each other? What was the buzzword? Orthogonal what? Complements, okay? And in essence, what I want you to remember is when you put the row space and the null space together, which space do you make? The whole of Rn. So effectively, if you have a basis for the null space, the way you calculate the free vectors, and you have a basis for the row space, if you put them together, so n vectors totally, that's a basis for Rn. That's what basically means that they're orthogonal complements. So what we're going to do today, I'm going to give you lots of homework problems, maybe too many that you think is too much for the homework, but I think it is the only way we can have enough problems that we check the different aspects of the course. So when you are ready to take the first prelim, you have something to work on, right? If I give you only 2 problems per homework, what do I supposed to ask you in the first exam? Okay, so you will see lots of problems, but remember, each of these problems is a few lines only. All right, if you write too much, means something is wrong. Okay, so the lecture today, lecture 12, will be to discuss about projections onto a subspace. So, you know, when we said, you remember we said that if you take any vector x in Rn, you can actually write it as a component in the row space and a component in the null space. That's what it means, orthogonal complements. The same way if you take a vector and you say, I'm going to take a vector in 2 dimensions, x, y, and I'm going to write it as an x component and a y component. So now I can write it in 2 components in 2 subspaces that are orthogonal complements of each other. And the question then that is posed is, how do I take a vector in Rn and actually find its projection in one of those subspaces? That's what we need to do today, okay? And you will see in an extremely natural way, with a rather simple algebra, this will lead to ideas of least squares that most probably you have used before in many courses, even in your labs, you know, when you collect experimental data, but most probably you don't understand where the mathematics of least squares come, and that's what we will do today. If there is one of the most fundamental problems in engineering and the sciences, right, something you will need to do regardless what your research area is least squares. So we need to talk about least squares. All right, so let me talk about orthogonal projections. And as always, the way our textbook, the book by Professor Strang always does in every chapter, he summarizes everything. So if you get the first slide, effectively you know what is coming, and the rest is just a a little bit of justifications here and there. So the first thing we're going to do is we are going to do projections in a line. So we're going to take a line that is parallel to this vector A, and we're going to project the vector B to that line, and we're going to calculate that the projection of B to the line A is given by this nice vector. Obviously, it's in the direction of the line A, times this coefficient that involves A transpose B divided by A transpose A. So we'll just do projections in a line, and we will derive this formula today. Now, if you do projection in a line, obviously, that projection, that point P, will be the nearest point to the line, the nearest point to the original point B that you started. So if you're looking for the nearest point on the line, that's the nearest point. That's the projection, right? If you want to find, if you have a point and you say, find me the nearest point to this plane, what do? You take a projection, right? Geometrically thinking. Now, this difference between B and this projection is basically the error that you're committing. And in the particular case of projection to a line, that error is going to be perpendicular to the line. Correct? You take a vector B, you project in a line, the error obviously is going to be perpendicular to the line. All right, so as a matter of fact, just to emphasize that this is perpendicular to A, you can write down Pythagorean theorem where you say the magnitude of P squared and the magnitude of the error squared is equal to the magnitude of B squared. So basically, you do orthogonal projection, and the magnitude of B squared is the magnitude of the projection plus the magnitude of the error square. We will see this, okay? Just projection in a line, nothing fancy. Then, if you can do a projection in a line, the question is, can you actually do projection in a subspace, let's say, of Rn or Rm, where it's not just a line, but is maybe a linear combination of different basis vectors? Maybe it's the column space of a matrix. How do we project a vector to the column space of a matrix? The ideas will be similar. We're going to compute a projection point P, and then B minus P is going to be the error. And the only thing we have to do is modify this formula here, right? This is only for projecting on a line. So if we project to a subspace, the equation will look very similar to this. So if you can project in a line, you can project to any subspace. The calculation actually will be only one line long, because the idea for a line or a subspace will be similar. Okay. Now, a fundamental part of that is going to come up from this projection in the column space of a matrix. This matrix A transpose A will be somehow the matrix that is coming in the model, okay? A transpose A, this is what you get naturally when you do this type of projections. And one fact that I am stating here, and it is in lecture 11, I took extra effort, actually, an extra 15 minutes to put everything about the discussion on this topic. The null space of A transpose A is the same as the null space of A. So if A is invertible, A transpose A is invertible, okay? I'm sorry, let me correct myself. Very wrong what I said. I mean, A doesn't have to be a square matrix to be invertible. So let me correct it and put it as follows. If A has independent columns, then A transpose A is invertible. This is what we will see today. The derivation is one line, but I want you to remember, because this is very, very fundamental in being able to do least squares analysis. So if A has independent columns, all right? So so the null space of this is basically 0, then A transpose A, that is always a square symmetric matrix, would be invertible. A doesn't have to be square. All right, so I said that we would be able to generalize this formula, and I happily now see that in the summary, this is the result we're going to get. And actually, if you look, looks almost identical to this result, but instead of that inner product A transpose B, we now have A transpose B. A is the matrix. instead of having A transpose A divided there, we have now A transpose A inverse. And instead of having that vector A, we have the matrix A. That's a nice projection of a vector to the column space of a matrix. All right? Have you seen that before? Anywhere? No? That's good. I don't want you to tell me that I keep doing things that you already know. So if you have not seen it and you see it for the first time, this is great. There is always a first time for learning things. All right, and we're going to define in this process what we call a projection matrix. So a projection matrix, basically P that you see here, it's a matrix that when we operate on the vector B, let's say in Rn, we get the projection on the column space of a matrix A. That's what a projection matrix, this is the definition. And we're going to prove basically, we don't even have to prove, we're going to see some fundamental properties of projection matrices. One of them will be that P squared, so P times P is equal to P. Can you guess, before we even do any algebra, why P squared is equal to P? So if P takes a vector and projects it on a subspace, why is P squared equal to P? Huh? Well, I don't say any identity there. I say P squared equal to P. So why, taking the projection twice, I get the projection itself? So you have a vector, let's say, and you project on this plane. So this vector is projected down there. If you do once more, if you project once more, this point on that plane, where is it going to go? In the same place. All right, because it's already on the plane. So that's where P squared equal to P is coming. OK, so let's do some examples. Trivial things, just geometrical, to get a sense of what is going on. I'm going to start with a vector in 3 dimensions, x, y, z. And I'm going to take a projection of this to the z-axis. I'm going to give you this matrix P1, what it looks like. But let's start with the result first. Will you agree that if you have a vector and you want to project in the z-axis, the projection is 0, 0, z? Right? Is that what we call projection? Yes? Thank you. I will pay you if you volunteer to say yes. OK? If this is what it takes. All right. Do you agree that the projection of this vector B to the plane xy is this vector xy0? All right. So now I'm going to ask you, what are the matrices actually P1 of B and P2 of B that actually do these projections? I mean, they are very elementary matrices. So hopefully the next slide will show us what these matrices are. Will you agree with me that these are looking naturally, the two projection matrices? Take P1, multiplied with the vector xyz, and tell me what you get. When you multiply P1 times a vector xyz, what do you get? 0, 0, z. And what do you get multiplying P2 with the vector xyz? You get xy, 0. OK? So this is sort of typical projections to, for 3-dimensional vectors. But obviously, we need to generalize this beyond 3 dimensions and being able to actually compute this. In this case, they're elementary matrices, so it's easy to see the answer. But we need to be able to compute this. All right, so this is P1 times B and P2 times B. They give me two projections. And I call, by the way, the projected vectors little p's. So capital P's will be the matrices. Little p's will be the projection vectors. All right, I want you, don't read anything on this slide. Let's concentrate only on the bottom, because this is an amazing result. Can somebody read this thing with words and tell me what these two equations mean? Because we're going to be using this idea all the time. So you remember we project it on the z-axis and we project on the xy plane. So what does it mean that B is equal to P1 plus P2? How do you understand this? Why is that the case? But be more linear algebra oriented, based on what we know. What is this equation saying? That we take this vector b in R cubed, and we do what? We project it in two subspaces that they are. What is the z-axis and the xy plane? Repeat even better. Orthogonal complements. Big difference. Okay? So basically we write B as P1 plus P2, and P1 and P2 are the projections in basically two orthogonal complements of R cubed. And obviously, if you substitute that P1 is equal to the projection matrix P1 times B, and this is the projection P2 times B equal to B, you can see that the sum, if you take basically the sum of the projections in orthogonal subspace, orthogonal complementary subspaces, you get the identity matrix. Right? So a vector here is a vector on this subspace, and this orthogonal complement and that, and if I put all together, I get the identity. I go back where I started, where I sum all of this. Okay? They look simple, trivial equations for our example, all right? But you know, we will actually generalize this to things that don't look necessarily trivial, so please do remember this type of formulas. All right, so now we're going to make life interesting. So no video games at this point, because this is a very critical point of the lecture today. So what we're going to do is we're going to try to project in a subspace that has a basis, and you know, we'll take a typical example, the column space of a matrix A. So we're going to project a vector in Rm to the column space of a matrix A, all right? And before I actually do it, okay, so here are three different matrices, all right? So this is, you know, with A1, we are projecting where? So when you look at the column space of this, just give me, if I take a vector in R cubed, where do I project? So this vector, this matrix has one column only. So if I project with this in this column space, x, y, z, what do I get back? Z. Okay, I get 0, 0, z. Okay, now look at this two matrices here, all right? How many independent columns they have? I mean, the column space is in R cubed, and each of them, how many independent columns it has? All right, so they have, you know, two independent columns. So effectively, if I try to project in the column space of A2 and the column space of A3, the answers will be the same. All right? So somehow, the calculations that we will do need to account, you know, for the fact that there are different bases of R2, but, you know, when we project on with this in this column space or that column space, we should expect to get basically the same projection points and also the same projection matrices. All right. So before I do the column space problem, let me do the algebra for the line, okay? And then we will generalize this formula for the line to the column space of any matrix A. So the calculations that you will see now, it's simple geometry on the plane, so nothing fancy. So here is, you know, I'm looking in R2. So that's my space, this plane, you know, on the screen there. So this is the vector B, and I want to do projections on a line parallel to this vector A, and I don't assume that A is a unit vector. All right, so A is any vector in this particular orientation, and I want to find the projection of B, the orthogonal projection of B to this line, and I call this orthogonal projection little p. Effectively, what I want to do is I want to prove this formula that I showed you before. Now, if you project orthogonally to this line A, the error that you have in approximating B with this projection P is obviously this vector E that you see here, which is B minus P. And what can we say about the error? That the error is what? I see here, the error is orthogonal to where? To the line that we do the projection. This is important. So when later on we generalize and we project on the subspace, the error will be orthogonal to that subspace. Here, the error is orthogonal to that line. So in principle, if we want to approximate B with some vector on the line, this is the best solution we can get, okay? And this error, there is nothing we can do about it. All right, there is nothing we can do about that error. All right, so let's derive this simple formula, okay? The error you just told, so let's, I'm gonna write this projection point P as x hat times A, where x hat is unknown. Are you fine with this formula? What does this formula say? Is that the projection vector has what orientation? When you look at that formula, it says the projection point P is in what direction? A. So what I say is, okay, it's going to have the orientation of A and some additional magnitude that I need to adjust. I have no idea what it is. So let's call it x hat. So this x hat actually is going to come in a major way to play a role in our calculations. But basically here is some scalar that when I multiply with the vector A, I get the projection vector P. So my error is really B minus x hat, that scalar, times A. We agree? All right. Now, what did we say a minute ago? That this error is perpendicular to what? This error is perpendicular to what? Tell me to what? The line A. And what does perpendicular means? That the inner product of A with that error has to be equal to 0. Correct? And again, I am going to apply the same calculation when we project in a subspace. So I'm going to be asking you these questions, where this comes, and you need to tell me, okay? So here I take the inner product with A, and this has to be equal to 0. So there I have A dot B, nice. And then I have A dot A. And I just said that we don't take A to be a unit vector. And times that scalar x hat. So x hat, what is it? A dot B divided by A dot A. And if I want to write this in a, explicitly in terms of vectors, A transpose B divided by A transpose A. Correct? So it's a number. I mean, this is what we get, right? A transpose B divided by A transpose A. So now we know everything. We know basically what the projection point P is, all right? We know what the error is because we have calculated this x hat, so we can do anything we want to. All right, so the projection of B in the line is this, okay? And I'm going to do two special cases. If B happens to be on that line, what do you think the projection of B is? If B is on that line, what's the projection of B? It's already on that line, so what's the projection of B? Don't look at the equations. If B is already on that line, and I want to project it to that line, what is the projection of B? B. Is that formula says that? So look at that thing. If B and A are the same, all right, A transpose B, A transpose A, cancel, and then I get A. And actually, you can try also to be 5 times A. You will see you will get back 5 times A because the scaling effects on A on this thing will cancel out. Okay? So the special case, if B is equal to A, then this x hat is equal to 1. And effectively, when you project something that's already on the line, you get back what you started with. So the projection metrics that I have not written yet down explicitly, in this particular case, would be the identity metrics. All right. Special case 2. If the vector B is perpendicular to the line, what this formula should give me, that the projection of a vector perpendicular to the line should be equal to 0. That says that? Well, yeah, if B is perpendicular to A transpose B is 0. Done. All right? And so the projection P is equal to 0. OK, so let's do it. Before I give you the projection metrics, let me give you an example. So if you have a vector B in R cube, and you want to project it on this vector A, basically you need to compute this scalar x. So if you plug in things in the formula A transpose B is equal to 5, A transpose A is equal to 9, and this ratio here is 5 over 9. So the projection point is 5 over 9 times A. OK, that's it. Now, if I go back for a second, maybe if you were in high school, right, and somebody says, I want to project this vector B to this vector A, you know what you will do is, you will say, oh, you know what, the magnitude of this vector is B times cosine of theta, and it's in the direction of the A vector, so times A divided by the magnitude of A, correct? It is not recommended to actually do this, because when you do that calculation, you will find out that calculating the magnitude of P involves square roots, calculating the cosine involves square roots, but actually, in this particular case, calculating this A transpose B over A transpose A, no square roots are involved. Of course, you get the same answer, but this is actually a more elegant way to do the calculation. No cosines. OK, we'll leave those behind us. Because remember, in this course, we are interested in concepts, not in square roots and cubic roots and things like that. Simple things. All right. So in this case, so the projection vector is this. And if you want to calculate the error, you take B minus the projection, so this is the error. And if you are curious, this error is supposed to be perpendicular to what vector? To the original vector A. What was A in this problem? I forgot. So A was 1, 2, 2. All right? So what's the projection of this? So is this vector normal to 1, 2, 2? It's supposed to be normal, right, to the vector A. Is it normal to 1, 2, 2? Actually, I have no idea why is that ugly 4 there. This is 4 over 9. And I know I changed it just before I came. OK? So this is 4 over 9, minus 1 over 9, and minus 1 over 9. So if I multiply this with 1, 2, 2, and take the dot product, what I get is 4 minus 2 minus 2. I get 0, as it's supposed to. OK? So this is supposed to be 4 over 9. OK? 4 over 9. All right. So so we did the projection, and the question now, because we need to introduce the concept of the projection matrix. You remember that by definition, the projection matrix, P, capital P, is the matrix that when I operate on B, I get this projection point P. So basically, I take B and I project it to that line to get this little p. So the question is, what is the projection matrix P? And I want you to look, don't look at this, pretend that it's not there. Look at this and tell me what's the projection matrix P. I don't see any metrics there, but maybe you can rearrange terms and you can see what the projection matrix is. The projection matrix is AA transpose divided by A transpose A. And AA transpose is a matrix of what rank? By the way, I put additional discussion in preparation for this on rank 1 matrices and some other comments on writing matrices in terms of rank 1 matrices. This matrix is of what rank? What is the column space of AA transpose? Just the vector A. What is the row space of AA transpose? Just the row A transpose. The vector A, basically. It's a rank 1 matrix. And actually, it's a particular rank 1 matrix because the column and row space are generated by the same vector A. Okay? So this is the projection to a line. AA transpose a matrix. A transpose A is a scalar. It's the inner product. This is the outer product, which is a matrix. So the projection in our case, if we're talking about vectors in Rm, it's a matrix that is m by m. So this matrix here is m by m. So literally, if you want to project to a line, you compute this projection matrix, capital P, and then you operate directly with that on B, and that's the answer. So you don't need any of these intermediate things because what you need is this projection. And I am sure you will come up in different subject areas in your courses with this type of projection matrices, AA transpose, all the time. And actually, you will come up all the time because there is a fundamental theorem that is posted on lecture 11 that says any matrix that has rank R can be written as the sum of R matrices, each of them having rank 1. This is an extremely fundamental result. Any matrix of rank R can be written as the sum of R rank 1 matrices. And later on, when we try to do approximations of matrices, we will try to actually do what's called reduced rank approximations. Very fundamental thing in applications. All right. So I compute this particular matrix in our example. If you put A is equal 1 to 2, 2. So this is the projection matrix, A transpose divided by A transpose A, which is equal to 9. And I get this matrix. And can you look now why I told you that is rank 1? All right? You don't have to wait to do the multiplication to know that's rank 1. But now that is there, what is there in the matrix that tells you that this is rank 1? How many independent columns? How many independent rows? 1. Okay? So this is a rank 1 matrix to do these projections. All right. And of course, we said P squared equal to P. Okay? And for those who don't believe me, please go ahead and just multiply this by P and see if you actually get the same matrix back. Because I'm not going to do the multiplication. I'm tired. Okay? But take the time, take P times P and see that you get P. Should be an interesting exercise, right? It's not obvious, is it? But once you know that's a projection matrix, you actually can trust it. You say, yep, I can see it. Now, let me tell you another thing that I want you to start thinking and extrapolating. And you can reason when you go home if it's a coincidence. If I sum the diagonal elements, what do I have? 4 plus 1, 9. Over 9, I have 1. Reason about that as well. Is that a coincidence? I'm going to leave it on the air. OK? All right. Or in the exam. Or both. All right? Or none. OK. OK, so the matrix P projects to the line, as we did. How about this matrix, A minus P? Where does it project? Is I minus P a projection matrix? So P projects on the line, right? We did the calculation. So how about I minus P? Does by any chance project somewhere else? Where does it project? If somebody tells me with words, it's not written there, is it? No. OK, with words. So here's a line A. We calculated basically the projection matrix to project things to this line. Now, I minus capital P, where does it project? So if I take any vector in R cube, and I do I minus P times that vector, where do I project? With words. no symbols, no equations. Where do I project? I minus capital P. If P projects to this line, you remember the orthogonal complements? And I said, we had a slide where we said P1 plus P2 equal to I. So I minus P here projects where? Here's my line. Where does it project? The plane perpendicular to that line. That's it. Right? So if you want to project, in this particular to a plane perpendicular to a line, you find the projection first in the line and then take I minus P, and with confidence, that has to project to the plane perpendicular to the line, to the orthogonal complement. Okay? Nothing funny about it or complicated. Okay, so let's go to the subspace problem. So we need now to project, we have n vectors in Rm, and we assume that they are the columns of some matrix. And because I want to get some concrete result, I am going to assume that these columns are independent. Okay? They're independent. I'm not saying that they form a basis for Rm, but they're independent. I have a matrix, and the columns A1 to AN of that matrix they are independent. So the matrix doesn't have to be squared or anything like that. All right. So what I want to do is I want to find the closest point, and I indicate this point with these vectors here, these scalars, x hat 1, this should be an n there, should correct it, okay? X hat n, all right? So I want to project, a given vector B in Rm, I want to project it to the column space. So basically to each of these vectors A1 to AN that define the subspace, the column subspace of the matrix A. All right? So I have basically not one vector. I have, I have a subspace that is defined by n vectors, and I want to project my vector B to that subspace. So you can think that subspace being a plane. I want to and that plane is defined by the vector A1 and the vector A2, and I want to project to that plane. But it doesn't have to be a plane, with two vectors. It can be a plane with n vectors, right? We're talking about dimensionality Rm here. So, I want to be able to project to the column space of these vectors. Can you tell me now, repeating the calculations we did for the line, all the algebra, all right? So what, the picture you have, the geometric picture you have in your head, that's the correct picture. So if you have a subspace of Rm and you want to project, how do you project? You will find the nearest point, and where is that nearest point? So if I have, here is my point B, and I want to project to this subspace, what do you think geometrically? What do you have in mind? Before in the line, we took the orthogonal projection. Here we will take also the orthogonal projection. All right, that's the nearest point to that subspace. So we will take the nearest point on the subspace, and if I can see only the equation. So what I'm going to do is, you remember every point on the column space is a linear combination of what? By definition. Every point in the column space is a linear combination of the column vectors, A1 to AN. So effectively, what I am going to, when I do the projection, right, the orthogonal projection, I am looking for a vector x hat, that's vector, all right, that defines AX hat. And what is AX hat? Is the orthogonal projection of B to that plane, to that subspace, right? When I project B on the subspace, I'm going to get some unknown combination of the columns. And I call that unknown combination AX hat. So really, AX hat is my projection point P. X hat is unknown. I don't know what it is. And again, the only thing I'm using here is every point on the column space, a combination of the columns. And you remember A times X there, right? A times X gives you combination of the columns. So I am saying find me a point on that subspace, all right? And that point, it's A times X hat, some combination of the columns. Now, I have not said anything yet about orthogonality, so I have not used that. So if I project to this point P, that is A X hat, can you tell me how much error then do I have? I started with B. I approximated with some linear combination of the columns. So what is the error that I do? So I start with B. I approximate it here with AX hat. So what's the error I do? B minus AX hat. Now I'm going to use the idea of orthogonality. That error, B minus X hat, needs to be orthogonal to where? To the column space. Correct? B minus X hat needs to be orthogonal to every column vector. Think of the plane, right? You have a vector A1, a vector A2, whatever defines that plane. The error is orthogonal, so the vector has to be orthogonal to every base vector in that space. Okay? And, all right, so basically we need the error. So let me write, so don't pay attention to the equations. Effectively what I need is, I need, if A1 is one column vector, AN, another one, I need A1 transpose B minus AX to be 0, etc., AN transpose B minus AX equal to 0. You agree? I mean, the error B minus AX hat has to be orthogonal to every base vector in that subspace. Right? I am actually going to throw here, because I think you're looking at me, spaced out. Here is the column space. Can you give me a name for the orthogonal complement of the column space? Because the fundamental theorem of linear algebra. So if this is the column space, what is the other orthogonal complement subspace? How do we call it? Say it again. Left null space. And what's the definition of the left null space? A transpose Y equal to 0. Guess what? A transpose the error equal to 0. So the error has to be on the left null space, because the left null space is the orthogonal complement of the column space. Done. That's least squares. You don't need me anymore. Okay? Look, so basically, this is the equation here, right? B minus AX belongs in the left null space, so A transpose B minus X is equal to 0, so A transpose A X hat equal to A transpose B, and that's basically the fundamental equation in least squares models. This is what people call the normal equations. And that's how this famous matrix A transpose A comes everywhere in engineering, in science, everywhere, right? A transpose A times X bar equal A transpose B. And of course, to be able to compute A transpose A, this needs to be, of course, it's an n by n matrix, it's symmetric, but to be invertible, we said, remind me, what's the condition for A transpose A to be invertible? That the columns of A need to be independent. Linear independent is even better. That's the correct terminology, okay? So they need to be linear independent, or the null space of A has to be the 0 vector. All right, so we started with that assumption that the columns are linearly independent, just to be sure that A transpose A is invertible. So X hat, I can solve for it. All right, where is my equation? Here is the equation. And again, there is a typo there. I need to go and correct it. So the typo here is A transpose A inverse outside, okay, times A transpose B, okay? And then if you're interested now to write down the projection point, what's the projection point? Is, you remember we're projecting to the column space, and we started with this definition of x hat, all right, the combination of the columns. So the projection point is A times x hat, which is A transpose A inverse, times A transpose B. We're done. I mean, that's the nearest point on the column space that approximates any vector B in Rm. And if somebody asks you, what is the projection matrix capital P? What are you going to say looking at this equation? What is the projection matrix capital P? By definition, the capital P, what is it? It's there. You remember, what's the projection matrix? You take the vector B, so capital P times B gives you the little projection point P. So what's the matrix? Everything except B. So the projection matrix is what you see there. And I know it maybe doesn't look to you like what we derive for the projection line, but to me it looks the same. What did we have for the line? Didn't we have little a transpose, and A transpose A was a scalar, and it was on the denominator? The same answer. But these matrices, you cannot go and exchange them, right? And don't ever write the inverse of this matrix as A inverse times A minus inverse transpose. Why? Because the matrix A is not invertible. Has independent columns, right? But that doesn't mean it's invertible. It may not be a square. So don't ever do any calculations for A transpose A inverse. You write it explicitly as A inverse A minus transpose. That's illegal, unacceptable. You can only do this if A is invertible. We're not interested in those simple problems. I mean, the whole idea, and we will see it, you know, on Wednesday, I suppose, of doing this type of least squares problems is we cannot solve AEX equal to B exactly. So we're trying to find some approximation where we try to sort of take an approximation of B to be in the column space, and then we can solve that problem. That's why we project B to the column space, so we can solve AEX equal B. Because in general, if B is not in the column space, what have we learned? If I give you AEX equal to B like in the homework, there is a problem, and B is not in the column space, there is no solution. There is no solution to that problem, but to this problem, AEX equal to P, where P is the projection of B in the column space, there is a solution to that problem. Okay? It's an approximate solution, but that's what we call the least square solution. So the projection matrix capital P is A transpose inverse, A transpose. All right, so here's the summary. The subspace we worked is the column space of A. Basically, we wrote a projection as a combination of the columns. That's where this AX hat came. We defined the error, B minus AX hat, and we said the error is perpendicular to the column space, so it has to be part of the left null space, and if it's part of the left null space, A transpose this equal to 0. That's why we learn about left and right and all of these things, right? There's a reason for that. It's not just to harass you with things that you will not ever use, okay? That's a question. Gives me basically X bar, and you have everything. You have the projection matrices, the projection point. And this equation basically that you see here, A transpose AX bar equal to A transpose B, these equations are known as the normal equations. So if you search on Wikipedia normal equations, you will immediately tell you least squares. Okay, that's the normal equations. Just to do an example, we have only 1 minute of why it is important for the columns to be independent. So here is, so I have a matrix A, right? Not invertible, you can see it's 3 by 2. and I have a B, can you see that this B, can you generate this B by taking linear combination of the columns? Is that B in the column space? Look at that B. Can you take combination of the columns and solve AX equal to B? No. We cannot do it, right? There's no solution. So what we will do is we will project B basically to the column space and solve the approximate problem AX hat equal to the projection point P. That's what gives us the least squares equations. So if you take A transpose A, you get this very nice symmetric matrix. If you take A transpose B, you get that. And the least square solutions basically in this case is X hat equal to 5 and minus 3. And remember, the projection point is a combination of the two columns. That's what X hat defines. So the projection point is 5, the first column, minus 3, the second, is the point 5, 1, minus 1. And the error is B minus P. So if you plug in P and you take your B that we started with, the error is 1 minus 2, 1. And you can check, that this point is actually on the left null space. So you can check that A transpose times this vector gives you a 0. Okay, and also, you can, if you want, you can check that this is directly orthogonal to each of the column vectors from the matrix A. And it's 1121, but let me just give you one rapid example, and then I am done, okay? So in this particular case, if you plug in the A that we started, and this is the projection matrix to the column space of A, you get this nice projection matrix, okay? This is how the projection matrix looks like. So you compute A transpose A, it's invertible, then you multiply on the left with A, on the right with A transpose, that's P, and you can check P squared is equal to P, again, no coincidence. And again, A transpose A in this case was invertible because the columns of A were independent. And I think in the slides, I have an example that I really want to show to you. Here's an example of a matrix A, okay? All right, here it is. So in this case, if you look at the two columns, one is a multiple, it's 2 times the second column, 2 times the first column. If you take A transpose A, you get this matrix. It looks nice, symmetric and everything, but it's not invertible. All right, so the columns of A need to be independent. And the slides that I just missed, they give you one more proof that you should read because it's very fundamental that it says A transpose A is invertible if and only if A has linearly independent columns. I discuss about this also in lecture 11, but everything you need to know is on those 2 slides. The proof is basically elementary. I always want you to remember A transpose A is invertible if A has independent columns. And never, never expand A transpose A inverse because that's a recipe for disaster. Okay? I know 1/3 of you will do that, but I told you, so don't ever. All right, see you Wednesday.